So here's something worth thinking about as you settle in tonight. Right now, as you're lying there, every single second, something like 65 billion tiny particles called neutrinos are passing through every square centimeter of your body. Every square centimeter. They're coming from the sun. They've traveled about 93 million miles to get here. And they're slipping through you like you aren't even there. Through the blanket, through the mattress, through the floor beneath you, through the entire earth itself, and out the other side without touching a thing. You can't feel them. You'll never feel them. And for most of human history, nobody had the faintest idea they existed. That's nuclear physics for you. It's the science of what's happening at scales so impossibly small that the entire width of a human hair might as well be the Grand Canyon. And yet everything depends on it. The light from the sun that woke you up this morning, the heat at the center of the earth that keeps the ground beneath your feet from freezing solid, the reason certain rocks are warm to the touch, the reason stars shine at all of it comes down to what's happening inside the nucleus of an atom, this almost incomprehensibly tiny speck at the center of something that's already too small to see. And the story of how we figured all of this out, how we went from not even knowing atoms were real to splitting them apart and unleashing energies that can power cities or destroy them, that story is one of the most extraordinary things human beings have ever done. It stretches across about 120 years. It spans wars and revolutions and quiet afternoons in basement laboratories, and it involves some of the most brilliant, stubborn, eccentric, tragic, and occasionally lucky people who ever lived. So let's start at the beginning, the real beginning. For most of history, the smallest piece of anything was whatever you could see when you broke it apart. You snap a stick, you get 2 smaller sticks. You grind a rock, you get sand. You keep going, and eventually the pieces are too small to see, but the general assumption was that matter was just continuous, smooth all the way down. Like cutting butter. You could always cut it thinner. But there was this nagging idea, going all the way back to ancient Greece, that maybe that wasn't true. Around 400 BC, a philosopher named Democritus, and probably his teacher Leucippus before him, proposed that if you kept cutting something smaller and smaller, eventually you'd reach a piece so small it couldn't be cut anymore. He called these pieces atomos, uncuttable. And he imagined that everything in the world was made of these tiny, indivisible particles, different shapes and sizes for different materials, bouncing around in empty space. Now, here's the thing about Democritus. He was basically right. 2,400 years before anyone could prove it, he had the core idea. But he couldn't prove it, and in the ancient world, that mattered less than having a more famous philosopher disagree with you. Aristotle thought the idea of empty space was nonsense. Nature abhors a vacuum, he said. And Aristotle's influence was so enormous that the atomic idea basically got shelved for about 2,000 years. 2,000 years. Think about that. One of the most important ideas in the history of science, just sitting in a drawer because the most popular philosopher in the Western world thought it sounded wrong. It wasn't until the early 1800s that atoms started to come back in a serious way. And the person who brought them back wasn't a philosopher this time. He was a chemist. John Dalton, working in Manchester, England, was studying how different gases combined with each other, and he noticed something peculiar. When elements reacted, they always combined in simple, whole number ratios. You'd get one part of this combining with one part of that, or one part with two parts, but never one part with 1.5 parts or 2 and 3/7 parts. Always clean, whole numbers. And Dalton realized that the simplest explanation for this was that matter came in discrete little packets. Atoms. If oxygen and hydrogen combine in a ratio of 1:2 to make water, that's because each unit of water is literally one atom of oxygen stuck to 2 atoms of hydrogen. Not a smooth blending, not a continuous mixture, but specific countable pieces clicking together like tiny building blocks. Dalton published his atomic theory in 1808, and it was elegant and useful, and it explained a lot of chemistry beautifully. But, and this is important, Dalton thought atoms were solid, indivisible, little billiard balls with no internal structure. The word atom still meant uncuttable, and Dalton took that literally. Whatever atoms were, they were the end of the line, the smallest possible thing. There was nothing inside them. For most of the 1800s, that was the working assumption. Atoms were real, they were small, they were the fundamental building blocks of everything, and that was that. Chemistry was making enormous progress by treating atoms as simple, featureless spheres that combined in predictable ways. Nobody had much reason to look deeper. But then things started getting weird. In the 1850s and 1860s, scientists started playing with glass tubes from which they'd pumped almost all the air out. Vacuum tubes. And when they ran electricity through these tubes, connecting a metal plate at each end to a high-voltage source, something strange happened. A glow appeared. A mysterious ray seemed to travel from the negative plate, called the cathode, toward the positive plate at the other end. They called these cathode rays, which is a wonderfully unhelpful name because nobody knew what they actually were. Were they a kind of light? Were they waves in the leftover gas? Were they something else entirely? This was genuinely controversial for decades. German physicists tended to think they were some kind of wave phenomenon. British physicists leaned toward the idea that they might be particles. And the argument went back and forth without resolution for almost 40 years. Then, in 1897, a man named Joseph John Thomson, everyone called him JJ, settled it. Thomson was working at the Cavendish Laboratory in Cambridge, which was already becoming one of the most important physics labs in the world. And what Thomson did was deceptively simple, but incredibly clever. He put those cathode rays through both electric and magnetic fields, and by carefully measuring how much the rays bent in each field, he could figure out the ratio of their electric charge to their mass. And here's what he found. Whatever these cathode ray particles were, they were light. Absurdly light. About 1,800 times lighter than a hydrogen atom, which was the lightest atom known. And they carried a negative electric charge. Think about what that means. If these particles were coming out of the metal cathode, and they were way smaller than any atom, then atoms weren't indivisible after all. There was something inside them, something smaller. Thomson had found a piece of the atom, and he'd proved that the thing Democritus said couldn't be cut, could be cut. Thomson called these particles corpuscles, which didn't stick. Everyone else started calling them electrons, a name that had actually been coined a few years earlier by an Irish physicist named George Johnstone Stoney for a theoretical unit of electric charge. And just like that, the atom had structure. It wasn't a featureless billiard ball. It had parts. But now there was a problem. A big one. If atoms contained these tiny, negatively charged electrons, and atoms as a whole were electrically neutral, which they clearly were, because matter doesn't normally zap you when you touch it, then there had to be something positively charged in there too, to balance things out. But what? And how was it all arranged? Thomson proposed what became known as the plum pudding model, which is one of the most charmingly British names for a scientific theory ever conceived. He imagined the atom as a sort of blob of positive charge, spread out evenly like the dough of a pudding, with the tiny electrons embedded in it like plums or raisins. Everything distributed smoothly, everything balanced, everything stable. It was a reasonable guess. It was elegant, and it was completely wrong. But we'll get to that. Because the experiment that destroyed the plum pudding model is one of the most famous experiments in all of physics, and it deserves its own space in this story. For now, let's stay with what the world looked like right around 1900, because this is a genuinely remarkable moment. In the span of just a few years, 3 separate discoveries landed almost on top of each other, and each one cracked open the door to nuclear physics a little wider. The first was Wilhelm Röntgen's discovery of X-rays in 1895. Röntgen was working with cathode ray tubes in Würzburg, Germany, and he noticed that even when he covered the tube with black cardboard, something was making a fluorescent screen across the room glow. Some kind of invisible ray was passing through the cardboard, through the air, through things that light couldn't pass through. He didn't know what they were, so he called them X-rays, X for unknown. And when he used them to take a photograph of his wife's hand, showing her bones and her wedding ring clear as day, the image electrified the entire world. Within weeks, doctors were using X-rays to find broken bones and bullets lodged in patients. Röntgen received the very first Nobel Prize in Physics in 1901. The second discovery came from Henri Becquerel in Paris in 1896. Becquerel was investigating whether certain minerals, after being exposed to sunlight, might emit X-rays. He was working with uranium salts, and his plan was to put the uranium on top of a photographic plate wrapped in dark paper, leave it in the sun, and see if the plate got exposed. But then the weather turned cloudy. Becquerel stuck the whole setup in a drawer and waited for sun. When he finally developed the plate a few days later, expecting to see nothing, no sunlight, no exposure, no result, the plate was fogged, strongly fogged. The uranium had exposed the photographic plate all by itself, sitting in the dark, without any sunlight at all. Something was coming out of the uranium spontaneously. Not X-rays triggered by sunlight, but some kind of radiation that the uranium was producing on its own, all the time, just by existing. Becquerel had discovered radioactivity, though he didn't call it that yet, and he was a little puzzled by it. But honestly, he didn't pursue it as aggressively as he might have. The person who really grabbed hold of this mystery and refused to let go was a young Polish-born physicist working in Paris named Maria Skłodowska. You know her as Marie Curie. Curie was looking for a doctoral research topic, which in the 1890s was an unusual thing for a woman to even be attempting. She'd come to Paris from Warsaw because Polish universities wouldn't admit women, and she'd been studying at the Sorbonne, often barely able to afford food, sometimes fainting in class from hunger. She was tough in a way that's hard to overstate. And when she heard about Becquerel's mysterious uranium rays, she decided that this was what she wanted to study. Working with her husband Pierre, who was already an accomplished physicist, Marie Curie began systematically testing every element and mineral she could get her hands on to see which ones emitted these rays. And she found something surprising. A uranium ore, called pitchblende, was more radioactive than pure uranium itself. that shouldn't have been possible. Unless pitchblende contained some unknown element that was even more radioactive than uranium. So the Curies set about trying to isolate it. And this is where the story becomes almost physically painful to hear about. They were working in a converted shed, basically a leaky, unheated former medical school dissection room, processing tons of pitchblende by hand, literally tons, grinding, dissolving, filtering, precipitating, over and over and over again. Marie did most of the physical labor herself, stirring massive vats of boiling chemical solutions with an iron rod, her hands cracked and burned from the chemicals and, though she didn't know it yet, from the radiation itself. By 1898, they'd found not one, but two new elements. The first they named polonium, after Marie's beloved homeland. The second they named radium, because of its intense radioactivity. Radium was extraordinary. It glowed in the dark. It was warm to the touch. It could burn skin, and gram for gram, it was roughly 1,000,000 times more radioactive than uranium. The Curies had no idea how dangerous it was. Marie used to carry test tubes of radium salts in her pockets, and she kept some by her bed at night because she liked watching it glow. Her laboratory notebooks from this period are still so radioactive that they're kept in lead-lined boxes, and you have to sign a waiver and wear protective clothing to look at them. But here's the question that radioactivity raised, and it's the question that would drive nuclear physics for the next several decades. Where was all this energy coming from? Radium was sitting there, emitting heat and light and radiation, hour after hour, day after day, year after year, with no apparent fuel source. It wasn't burning. It wasn't connected to anything. It was just radiating, and the amount of energy was staggering. Pierre Curie calculated that a gram of radium gave off enough heat to melt its own weight in ice in about an hour. Continuously. For years. This violated everything anyone thought they knew about energy. The law of conservation of energy said energy couldn't just appear from nowhere. So where was it coming from? What was happening inside those atoms? What was the source of this seemingly inexhaustible power? The answer, when it finally came, would reshape the entire world. But getting there required someone to first figure out what the inside of an atom actually looked like. And that brings us to a laboratory in Manchester, England, around 1909, where a New Zealand-born physicist named Ernest Rutherford was about to fire tiny projectiles at a piece of gold foil and discover something so unexpected that he later said, "It was as if you'd fired a 15-inch artillery shell at a piece of tissue paper and the shell came back and hit you." That's a direct quote, by the way, or very close to one, and it gives you a sense of just how shocked he was. So let's slow down and really sit with this experiment, because it's one of those rare moments in science where a single result changes the picture completely. Rutherford had been working with radioactivity for years by this point. He'd already done foundational work classifying the different types of radiation. He was the one who named alpha rays and beta rays, based on how easily they could be stopped. Alpha particles, he'd figured out, were relatively heavy, positively charged, and moving fast. Beta particles were lighter, negatively charged, essentially high-speed electrons. And then there were gamma rays, which were even more penetrating, a kind of electromagnetic radiation. Rutherford was brilliant, loud, confident, and had enormous physical energy. He'd grown up on a farm in New Zealand, won a scholarship to Cambridge, worked under J.J. Thomson, and by 1907 he'd moved to the University of Manchester, where he had his own lab and a growing team of researchers. Now, the prevailing model of the atom at this time was still Thomson's plum pudding idea, that diffuse cloud of positive charge with electrons sprinkled through it like raisins in a cake. And Rutherford wanted to test it. His method was beautifully direct. He would use alpha particles as tiny bullets and fire them at things to see what happened. If Thomson's model was right, and atoms were these soft, spread-out blobs of charge, then alpha particles should pass through thin material with only slight deflections. It would be like rolling a bowling ball through fog. The fog might slow it down a tiny bit, but it shouldn't change its direction much. So Rutherford set two of his researchers on the task: Hans Geiger, a German physicist who would later invent the Geiger counter, and Ernest Marsden, who was still an undergraduate at the time, just 20 years old. Think about that. One of the most important experiments in the history of physics, and one of the key people doing the hands-on work, was essentially a college student. Rutherford had a gift for recognizing talent and putting people to work on exactly the right problem. The setup was elegant in its simplicity. They had a small radioactive source, radon gas, which emits alpha particles, aimed at a very thin sheet of gold foil. Gold was chosen because you can hammer it incredibly thin, just a few hundred atoms thick, and because it's a heavy element with a high atomic number, which would make any effects more pronounced. On the other side, they had a zinc sulfide screen, a surface that would produce a tiny flash of light, a scintillation, each time an alpha particle struck it. Geiger and Marsden would sit in a darkened room, eyes fully adjusted to the dark, and count these flashes one by one through a microscope, hour after hour, in the dark, counting tiny pinpricks of light. It was painstaking, tedious work, and at first the results were exactly what you'd expect from the plum pudding model. Most alpha particles went straight through the gold foil with little or no deflection. Some were deflected by small angles, a degree or two. All perfectly consistent with a soft, diffuse atom. But Rutherford, being Rutherford, suggested they check something. He told Marsden to look for alpha particles that had been deflected at large angles, scattered backward, essentially. According to the plum pudding model, this should basically never happen. There was no mechanism for it. A diffuse cloud of charge couldn't produce a strong enough force to knock a fast-moving alpha particle backward. It would be like throwing a tennis ball at a curtain and having it bounce back at you. But that's exactly what happened. Some alpha particles, a very small fraction, roughly 1 in 8,000, were coming back at angles greater than 90 degrees. Some were bouncing almost straight back toward the source. And this is when Rutherford made his famous artillery shell remark. It was impossible under the plum pudding model. Completely impossible. He spent months thinking about what could explain it. And the answer he arrived at, which he published in 1911, was radical. The atom wasn't a diffuse blob at all. Almost all of the atom's mass and all of its positive charge was concentrated in a tiny, incredibly dense core at the center, what Rutherford called the nucleus. The electrons orbited around this nucleus at relatively large distances, and the vast majority of the atom's volume was empty space. That's why most alpha particles sailed right through. They never got close to the nucleus. But on those rare occasions when an alpha particle happened to be aimed almost directly at a nucleus, it encountered this intense concentration of positive charge, and the electrostatic repulsion was strong enough to deflect it sharply, even send it bouncing backward. Here's what's really striking about this. The nucleus, Rutherford calculated, was something like 10,000 times smaller than the atom itself. To put that in perspective, if you blew an atom up to the size of a football stadium, the nucleus would be about the size of a marble sitting on the 50-yard line. And that marble would contain 99.9+% of the entire mass of the atom. Everything else, the electrons, the space they move through, is essentially nothing. Empty space. You, me, the bed you're lying on, the walls around you. We're almost entirely empty space. The solid feeling of the world is an illusion created by electromagnetic forces between atoms. The actual matter is these tiny, unimaginably dense specks. Now, Rutherford's nuclear model was a huge leap forward, but it immediately created a serious problem. And it's worth pausing on this because it shows how science actually works. You solve one puzzle and immediately create 3 new ones. The problem was this: if electrons are orbiting the nucleus like planets orbiting the sun, classical physics says they should be constantly radiating energy. A charged particle moving in a curved path emits electromagnetic radiation. That's just Maxwell's equations, well-established physics. And if the electron is radiating energy, it's losing energy, which means its orbit should decay. It should spiral inward, closer and closer to the nucleus, radiating faster and faster as it goes, until it crashes into the nucleus in a tiny fraction of a second. By classical calculation, every atom in the universe should collapse in about 100 millionth of a second. Obviously, atoms don't do this. You and I exist. Matter is stable. So something was deeply wrong with the classical picture. And this is where a quiet, thoughtful Danish physicist enters the story. Niels Bohr arrived in Manchester in 1912, fresh from Copenhagen, and he came specifically to work with Rutherford. Bohr was a fascinating character, tall, soft-spoken, sometimes maddeningly vague in conversation, but possessed of a deep physical intuition that bordered on the uncanny. Where Rutherford was loud and direct, Bohr was contemplative and circuitous. He would start sentences and trail off, rethink mid-thought, and sometimes take so long to formulate an idea that people wondered if he'd fallen asleep. But when the idea finally emerged, it was usually profound. Bohr looked at Rutherford's atom and saw the instability problem, and he did something bold. He essentially said, "Classical physics doesn't work here. We need new rules." And the new rules he proposed, published in 1913, were strange and radical. He said that electrons could only orbit the nucleus at certain specific distances, certain allowed orbits, certain energy levels, not any orbit, the way a planet could orbit a star at any distance, only particular ones. And when an electron was in one of these allowed orbits, it simply did not radiate energy, despite what classical physics predicted. It just didn't. He couldn't fully explain why. He just asserted it as a postulate, and then he added a second crucial idea. An electron could jump from one allowed orbit to another, but only by absorbing or emitting a very specific amount of energy, a quantum of energy, equal to the difference between the two energy levels. This was building directly on work by Max Planck and Albert Einstein. Planck had proposed back in 1900 that energy came in discrete packets, quanta, to solve a problem in thermal radiation, and Einstein had extended the idea in 1905 to explain the photoelectric effect, arguing that light itself came in quanta, which we now call photons. Bohr took this quantum idea and applied it to the structure of the atom itself. And here's what's beautiful about it. His model immediately explained something that had puzzled physicists and chemists for decades. It explained why each element produces its own unique pattern of spectral lines. You've probably seen this, even if you didn't know the physics behind it. When you heat a gas, hydrogen say, and look at the light it emits through a prism, You don't see a continuous rainbow. You see individual bright lines at very specific wavelengths. Hydrogen always produces the same lines: a red one, a blue-green one, a couple of violet ones, always the same. Every element has its own unique fingerprint of spectral lines. Scientists had catalogued these lines meticulously for decades, and Johann Balmer had even found a mathematical formula in 1885 that predicted the wavelengths of hydrogen's visible lines. But nobody knew why. It was just a pattern without an explanation. Bohr's model provided the explanation. Each spectral line corresponded to an electron jumping from one specific allowed orbit to another. The wavelength of the emitted light was determined by the energy difference between those two orbits. And when Bohr plugged in the numbers, using Planck's constant and the known charge and mass of the electron, his predicted wavelengths matched the observed spectral lines of hydrogen almost perfectly. It was a stunning confirmation. The atom had a quantized structure. Energy inside the atom came in discrete steps, not continuous flows. But even as Bohr's model was being celebrated, there were people who recognized its limitations. It worked beautifully for hydrogen, which has just one electron. But for heavier atoms with multiple electrons, it started to break down. The predicted spectral lines didn't quite match observations, and the model had a strange, almost ad hoc quality. Bohr had essentially declared that certain classical rules didn't apply at the atomic scale without being able to say what the deeper rules actually were. It was a brilliant patch, a bridge between the classical world and something new, but it wasn't the final answer. The final answer would require an entirely new framework of physics, one that would take another decade to emerge and would be stranger than almost anyone imagined. Meanwhile, though, Rutherford wasn't done making discoveries. In 1917, he did something that alchemists had dreamed about for centuries. He actually transformed one element into another. He was bombarding nitrogen gas with alpha particles, and he noticed that the collisions were producing hydrogen nuclei, protons. What was happening was that the alpha particle was hitting a nitrogen nucleus hard enough to knock a proton out of it, transforming the nitrogen into oxygen. It was the first artificial nuclear reaction in history. Rutherford had split an atom, or more precisely, he'd chipped a piece off one. And from this work, he concluded that the hydrogen nucleus, a single proton, was a fundamental building block of all atomic nuclei. He named it the proton in 1920. But there was a puzzle. If nuclei were made of protons, then the mass should equal the number of protons times the proton mass. And it didn't add up. Helium, for instance, has an atomic number of 2 protons, but its atomic mass is 4, not 2. Something else was in there, contributing mass, but no electric charge. Rutherford actually predicted in 1920 that there must be a neutral particle inside the nucleus, something with roughly the same mass as a proton, but no charge. He even suggested a name for it. But proving it existed would take another 12 years, and the person who finally found it was James Chadwick, a quiet, meticulous physicist who had been Rutherford's student and closest collaborator for years. Chadwick was the kind of scientist who doesn't always get the spotlight, partly because he wasn't flashy. He wasn't a showman. He was patient, careful, and deeply methodical. And he had been thinking about Rutherford's hypothetical neutral particle for over a decade. Imagine that. 12 years of carrying an idea around in your head, knowing it should exist, waiting for the right experiment, the right clue, the right moment to prove it. And the clue, when it finally came, arrived from an unexpected direction. In 1930, 2 German physicists, Walter Bethe and Herbert Becker, were bombarding beryllium with alpha particles and noticed that it produced an unusually penetrating form of radiation. They assumed it was gamma rays, high-energy photons, because it had no electric charge and could pass through thick materials. Then in early 1932, Irène Joliot-Curie and her husband Frédéric, Irène being the daughter of Marie and Pierre Curie, which is a wonderful bit of generational continuity in this story. They repeated the experiment and found that this mysterious radiation could knock protons out of paraffin wax. They still called it gamma radiation. But here's the thing. When you actually did the math on the energy required for a gamma ray to knock a proton forward with that much momentum, the numbers were absurd. The gamma rays would have needed impossibly high energy. Something didn't add up. Chadwick read their paper and immediately knew what was going on. He later said he couldn't sleep that night. Within about 3 weeks, he designed and ran a series of elegant experiments to prove that what was being emitted wasn't gamma radiation at all. It was a stream of particles with roughly the same mass as a proton but no electric charge. Neutral particles. Neutrons. He published his results in February 1932 in a paper titled simply Possible Existence of a Neutron, which is one of the great understatements in the history of science. There was nothing possible about it. He had it nailed, and this discovery changed everything. Not in some abstract philosophical way, in a very concrete, practical way, because now you could finally understand why atomic masses didn't match atomic numbers. Helium has 2 protons and 2 neutrons, giving it a mass of 4. Carbon has 6 protons and 6 neutrons, mass 12. The periodic table suddenly made deeper sense. But more than that, the neutron turned out to be the key that would unlock nuclear energy, nuclear weapons, and the entire modern era of nuclear physics. And the reason is beautifully simple. Because the neutron has no charge, it isn't repelled by the positive charge of atomic nuclei. You can fire a neutron at a nucleus, and it will sail right in, like rolling a ball through an open door. Whereas a proton or an alpha particle has to fight against enormous electrostatic repulsion to get close. The neutron was the perfect projectile for probing and splitting atoms. Chadwick won the Nobel Prize in 1935 for this, and he absolutely deserved it. Now, 1932 was an extraordinary year in physics. It's sometimes called the annus mirabilis of nuclear physics, and for good reason. In addition to Chadwick's neutron, Carl Anderson at Caltech discovered the positron, the antimatter counterpart of the electron, confirming a wild prediction that Paul Dirac had made a few years earlier using his relativistic quantum equation. John Cockcroft and Ernest Walton, working in Rutherford's Cavendish Laboratory in Cambridge, built the first particle accelerator to artificially split an atomic nucleus. They used a high-voltage machine to accelerate protons and smashed them into lithium, splitting lithium atoms into pairs of helium nuclei. It was the first time a nucleus had been split using a machine rather than relying on naturally occurring radioactive particles. And here's a lovely detail. When they measured the energy released by splitting the lithium, it matched Einstein's E equals mc squared almost perfectly. The mass of the products was slightly less than the mass of the original lithium plus the proton, and that missing mass had been converted into kinetic energy, exactly as Einstein's equation predicted. It was one of the first direct, quantitative confirmations of mass-energy equivalence in nuclear reactions. Think about that. An equation written on paper in 1905 by a patent clerk in Bern, verified in a laboratory in Cambridge 27 years later by smashing atoms apart. So by the early 1930s, the basic picture of the atom was coming into sharp focus. You've got a nucleus made of protons and neutrons, collectively called nucleons, bound together by some very strong force, surrounded by electrons in quantum mechanical orbitals. The strong nuclear force, as it came to be called, was clearly immensely powerful. because it had to overcome the electrostatic repulsion between all those positively charged protons crammed into a space about 100,000 times smaller than the atom itself. Imagine squeezing a bunch of magnets together with the same poles facing each other. They desperately want to fly apart. Something has to hold them together, and that something is the strong force, which operates only at extremely short ranges, basically the width of the nucleus itself. But within that range, it's the most powerful force in nature. Now, here's where the story takes a turn that would reshape the entire world. In 1934, the Italian physicist Enrico Fermi, one of the most brilliant and versatile physicists of the 20th century, started systematically bombarding every element he could get his hands on with neutrons. He was methodical about it, working his way through the periodic table, and he discovered something remarkable. Slow neutrons were actually more effective at inducing nuclear reactions than fast ones. This was counterintuitive. You'd think a faster projectile would be more effective, right? But Fermi realized that a slow neutron spends more time in the vicinity of a nucleus, giving it a better chance of being captured. It's a bit like the difference between throwing a ball past someone versus gently rolling it toward them. The slow roll gives them more time to catch it. Fermi and his team in Rome would slow down their neutrons by passing them through paraffin or water, materials rich in hydrogen, whose light nuclei would absorb energy from the neutrons through collisions. The way a billiard ball transfers energy when it hits another ball of similar mass. There's a famous story about how Fermi discovered this almost by accident. He was about to place a lead block in front of his neutron source as a filter, and at the last moment, on a hunch he couldn't fully explain, he substituted a piece of paraffin instead. The results were dramatically different. The reaction rates shot up. Fermi later said he had no rational reason for making the switch. Sometimes intuition in physics is a real, almost physical thing, a feeling in your gut that something is worth trying. When Fermi bombarded uranium, element 92, the heaviest naturally occurring element, with these slow neutrons, he got results he couldn't fully explain. He thought he had created new elements heavier than uranium, transuranic elements, elements 93 and 94. He published papers claiming as much, and it was exciting work. He won the Nobel Prize in 1938 partly for this research. But here's the thing. He was wrong about what was actually happening. Not wrong about the observations, but wrong about the interpretation. What was really going on inside those uranium nuclei was something far more dramatic and far more consequential than anyone realized. The person who figured it out was Lise Meitner, and her story is one of the most important and most unjustly overlooked in the history of science. Meitner was an Austrian-born physicist who had been working in Berlin for over 30 years. She was one of the leading nuclear physicists in the world, and she had been collaborating with the chemist Otto Hahn for most of her career. They were an extraordinary team. She provided the physics insight. He provided the chemistry expertise. Together, they had been repeating and extending Fermi's uranium experiments, trying to identify the products of neutron bombardment. But Meitner was Jewish, and when Nazi Germany annexed Austria in March 1938, she suddenly lost her Austrian citizenship protections and was in immediate danger. She fled Germany in July 1938, carrying almost nothing, smuggled across the Dutch border with the help of colleagues. She eventually settled in Sweden, at a small institute in Stockholm, isolated from her laboratory, her collaborators, and her life's work. It was a devastating upheaval. She was 60 years old. Meanwhile, back in Berlin, Hahn and his assistant Fritz Strassmann continued the uranium experiments. And in December 1938, they got a result that baffled them completely. When they bombarded uranium with slow neutrons, the chemical analysis showed that one of the products was barium, element 56. Barium has roughly half the atomic mass of uranium. This made no sense under any existing model. You don't chip a tiny piece off a heavy nucleus and get something half its size. That's not chipping. That's splitting the thing in two. Hahn was confused and a little frightened by his own results. He wrote to Meitner, who was spending Christmas with her nephew Otto Frisch, also a physicist, in the Swedish village of Kungälv. And this is one of those moments in the history of science that feels almost cinematic. It's the holiday season. There's snow on the ground, and Meitner and Frisch are walking through the woods, and she's telling him about Hahn's letter, and together, sitting on a log, or maybe it was a tree stump, the accounts vary slightly, they worked out the physics of what was happening. Meitner recalled the liquid drop model of the nucleus, which had been proposed by George Gamow and refined by Niels Bohr. In this model, the nucleus behaves a bit like a drop of liquid, held together by surface tension, the strong nuclear force, but also being pushed apart from within by the electrostatic repulsion of all those protons. For lighter elements, the strong force wins easily. But for very heavy elements like uranium, with 92 protons all repelling each other, the nucleus is barely holding itself together. It's like an overfull water balloon, quivering, on the edge of breaking apart. And when a neutron is absorbed, it can add just enough energy to set the nucleus oscillating, stretching into an elongated shape, and if it stretches far enough, the electrostatic repulsion in the narrow neck overwhelms the short-range strong force, and the whole thing snaps in two. Two smaller nuclei fly apart with tremendous energy. Meitner did a quick calculation right there, on the spot. She estimated the energy released by comparing the total mass of the products to the mass of the original uranium nucleus, using Einstein's mass-energy equivalence. The missing mass corresponded to roughly 200 million electron volts of energy, an enormous amount for a single atomic event, about 1 million times more energy than a typical chemical reaction. Frisch was stunned. He went back to Copenhagen, confirmed the physics with Bohr, and coined the term fission, borrowing it from biology, where it describes a cell dividing in two. And here's the detail that would change the course of human history. When uranium fissions, it doesn't just split into two smaller nuclei. It also releases 2 or 3 free neutrons, and those neutrons can go on to strike other uranium nuclei, causing them to fission as well, releasing more neutrons, which cause more fissions, which release more neutrons. A chain reaction. If you have enough uranium packed closely enough together, a critical mass, the reaction becomes self-sustaining. And if it's uncontrolled, it happens in a fraction of a second, releasing an almost incomprehensible amount of energy, all at once. Niels Bohr arrived in New York in January 1939, carrying news of the fission discovery, and within weeks, physicists across America and Europe had confirmed it in their own laboratories. The implications were immediately obvious to almost everyone in the field. Leo Szilard, a Hungarian-born physicist who had actually patented the idea of a nuclear chain reaction back in 1933, years before fission was even discovered, was particularly alarmed. Szilard understood, perhaps more clearly than anyone, that this discovery meant a bomb of unimaginable power was theoretically possible, and he understood that German physicists knew it too. The world was on the brink of war, and the most destructive weapon ever conceived was suddenly within reach. Szilard was not the kind of person who waited for someone else to act. He'd fled Berlin in 1933, the day after the Reichstag fire, literally packing his bags and catching a train before most of his colleagues had even processed what was happening politically. He had a gift for seeing around corners, for understanding where events were heading before they got there. And now, in the spring of 1939, he saw something terrifying. A straight line from Hahn and Strassmann's laboratory in Berlin to a weapon that could flatten a city. He also saw that the uranium ore most readily available in large quantities came from the Belgian Congo, and that if Germany moved quickly, they could secure that supply. So Szilard did something remarkable. He went to find Albert Einstein. Now, Einstein and Szilard actually knew each other. They'd collaborated years earlier on a refrigerator design, of all things, a pump with no moving parts. But this visit in the summer of 1939 was about something far more consequential. Szilard, along with fellow Hungarian physicists Eugene Wigner and Edward Teller, drafted a letter to President Franklin Roosevelt. Einstein signed it. The letter, dated August 2, 1939, warned that recent research on nuclear chain reactions made it conceivable that extremely powerful bombs could be constructed, and it urged the United States government to secure uranium supplies and fund research into this new phenomenon. The letter also explicitly noted that Germany had stopped the sale of uranium from Czech mines it had seized, a sign that German scientists might already be working on the problem. Think about the weight of that moment. A letter from the most famous scientist in the world warning the president that the fundamental structure of matter could be weaponized. Roosevelt received the letter in October 1939, a month after Germany invaded Poland and World War II began in Europe. He appointed an advisory committee on uranium, which held its first meeting on October 21st, 1939. But here's the thing. The committee moved slowly, agonizingly slowly from Szilard's perspective. The initial funding was modest, just $6,000 for neutron experiments. The bureaucracy didn't yet grasp the urgency. It would take nearly 2 more years and a critical report from British scientists before the American effort truly accelerated. That British report deserves its own moment in this story because it fundamentally changed the calculation. In the spring of 1940, 2 refugee physicists working at the University of Birmingham, Rudolf Peierls and Otto Frisch, the same Frisch who had worked out the fission theory with his aunt Lise Meitner, sat down and asked a very specific question. Not whether a bomb was theoretically possible, but how much uranium-235 you would actually need to make one. See, by this point, Niels Bohr and John Wheeler had worked out that it was specifically uranium-235, the rare isotope making up only about 0.7% of natural uranium, that was responsible for fission with slow neutrons. The much more abundant uranium-238 tended to absorb neutrons without fissioning. So the question was, if you could somehow separate out pure uranium-235, how much would you need for a critical mass? The prevailing assumption, the one floating around in most physicists' minds, was that you'd need tons of the stuff, an impractical amount. But Peierls and Frisch actually did the math carefully, using newly available data on neutron cross-sections, and they got a startling answer. Not tons, pounds. Their estimate was roughly 1 kilogram, maybe up to 10 kilograms. The actual number turned out to be closer to 50 kilograms for a bare sphere, but even their rough estimate was enough to demonstrate that a bomb was not just theoretically possible, but practically achievable. They wrote it up in a brief memorandum, the Frisch-Peierls memorandum, just a few pages long, and it laid out not only the critical mass estimate, but also the expected explosive yield, the radiation effects, and even some thoughts on how isotope separation might be accomplished. It was clear, precise, and absolutely chilling. This memorandum made its way to the MAUD Committee, a British group tasked with evaluating the feasibility of an atomic bomb. The name MAUD, by the way, came from a telegram Bohr had sent from occupied Denmark that ended with the puzzling phrase, "Tell Cockcroft and Maud Ray Kent." The British spent months trying to decode this as a secret message. Turns out Maud Ray was simply the name of a former governess who lived in Kent, but the committee kept the name anyway. And by the summer of 1941, the Maud Committee delivered its final report concluding that a uranium bomb was not only feasible, but could be ready in time to affect the outcome of the war. This report, when it reached the Americans, was the catalyst that transformed a modest research program into something unprecedented in human history. In October 1941, Roosevelt authorized an all-out effort. After Pearl Harbor in December, the urgency became absolute. By the summer of 1942, the project was placed under military control, and the Army Corps of Engineers established the Manhattan Engineer District, which is where the name Manhattan Project comes from, though most of the work happened nowhere near Manhattan. The military director was Brigadier General Leslie Groves, a blunt, demanding Army engineer who had just finished overseeing construction of the Pentagon. Groves was not a scientist. He was a builder, an organizer, a man who got things done through sheer force of will and an almost frightening capacity for managing complexity. And one of his first and most consequential decisions was choosing the scientific director of the project. He chose J. Robert Oppenheimer. Now, Oppenheimer was a surprising pick, and almost everyone thought so at the time. He was a theoretical physicist, not an experimentalist. He had never run a large organization. He had past associations with Communist Party members, including his brother and his former girlfriend, which made him a security risk in the eyes of many. But Groves saw something in Oppenheimer that others missed. A brilliant, charismatic intellect who could speak the language of every branch of physics, who could hold the entire problem in his head at once, and who could inspire and manage the extraordinary collection of talent that the project would require. Groves was right. Oppenheimer turned out to be perhaps the most effective scientific leader of the 20th century, at least for those intense, compressed years. Oppenheimer insisted on gathering the best physicists in one place, a dedicated laboratory where they could work together, share ideas freely, and solve problems in real time rather than through correspondence scattered across dozens of universities. The site he chose was a remote mesa in northern New Mexico, near a boys' school called Los Alamos Ranch School. The location offered isolation, security, and enough space to build what would essentially become a secret city. By the spring of 1943, scientists and their families were arriving at Los Alamos, given P.O. Box 1663 in Santa Fe as their mailing address, their real work hidden behind layers of secrecy. But here's the thing. Building a bomb wasn't just one problem. It was dozens of interlocking problems, any one of which could have stopped the entire project cold. And the first, most fundamental challenge was getting enough fissile material. Remember, natural uranium is overwhelmingly uranium-238. Only that tiny fraction, 0.7%, is uranium-235, the isotope that fissions readily. And chemically, the two isotopes are identical. They're both uranium. They behave the same way in chemical reactions. The only difference is mass. Uranium-235 has 3 fewer neutrons than uranium-238, making it about 1% lighter. Separating them is like trying to sort identical-looking marbles that differ in weight by 1%, at an industrial scale, to weapons-grade purity. Multiple approaches were pursued simultaneously because nobody knew which one would work best, and there wasn't time to try them sequentially. Gaseous diffusion, which involved converting uranium to a gas, uranium hexafluoride, and forcing it through thousands of barriers with microscopic pores. The slightly lighter uranium-235 molecules would pass through each barrier just a tiny bit faster. So by repeating the process thousands of times in series, you could gradually enrich the concentration. Electromagnetic separation, developed by Ernest Lawrence at Berkeley using his cyclotron expertise, essentially bent streams of uranium ions in a magnetic field, and the lighter uranium-235 ions followed a slightly tighter curve, allowing them to be collected separately. And thermal diffusion, a third method that exploited the tendency of lighter isotopes to concentrate near a hot surface when a temperature gradient is applied. Each of these methods was scaled up to an almost absurd degree at a sprawling complex in Oak Ridge, Tennessee. The gaseous diffusion plant alone, called K25, was the largest building under one roof in the world at the time, half a mile long, shaped like a U. Tens of thousands of workers operated these facilities, most of them having no idea what they were actually producing. They knew their specific task: maintain this pump, monitor that gauge. But the larger purpose was classified. The secrecy was extraordinary, and it mostly held. Meanwhile, there was a parallel path to the bomb that didn't require isotope separation at all. This is where Enrico Fermi comes back into the story, and where the concept of a nuclear reactor becomes central. Remember Fermi's neutron bombardment experiments in Rome, the ones where he thought he'd created transuranic elements? Well, it turned out that when uranium-238 absorbs a neutron without fissioning, it becomes uranium-239, which is unstable. It undergoes beta decay. A neutron converts into a proton, spitting out an electron, and transforms into element 93, neptunium. And neptunium itself is unstable, undergoing another beta decay to become element 94. This new element was discovered in 1940 by Glenn Seaborg and his team at Berkeley, and they named it plutonium. And here's what made plutonium so important. Like uranium-235, plutonium-239 is fissile. It can sustain a chain reaction. It can be used in a bomb. And because it's a different element from uranium, not just a different isotope, it can be separated chemically, which is vastly easier than isotope separation. But to make plutonium, you need a nuclear reactor. You need a controlled, sustained chain reaction in uranium, where some of the uranium-238 absorbs neutrons and transmutes into plutonium, which you then extract chemically. And that's exactly what Fermi set out to build. On December 2nd, 1942, beneath the stands of the abandoned football stadium at the University of Chicago, Fermi's team achieved the world's first self-sustaining nuclear chain reaction. The reactor was called Chicago Pile 1, a carefully engineered stack of uranium metal, uranium oxide, and graphite blocks. The graphite served as a moderator, slowing down the neutrons so they'd be more likely to cause fission in uranium-235, just as Fermi's paraffin had done years earlier in Rome. Control rods made of cadmium, which absorbs neutrons voraciously, could be inserted or withdrawn to regulate the reaction rate. The moment the control rods were pulled out far enough, the neutron count on the instruments began to climb steadily, not spiking and falling, but rising and holding. A sustained chain reaction. Fermi watched the instruments with characteristic calm, let the reaction run for about 28 minutes, then ordered the control rods reinserted. Arthur Compton, who oversaw the Chicago work, called James Conant in Washington with a coded message. "The Italian navigator has just landed in the New World." Conant asked, "How were the natives?" Compton replied. Very friendly. It's a charming little exchange, but what it represented was staggering. For the first time, humans had unlocked and controlled the energy inside the atomic nucleus. And the reactor wasn't just a proof of concept. It was the first step toward producing plutonium at scale. That scale-up happened at a place called Hanford, in the remote desert of eastern Washington state, along the Columbia River. Enormous production reactors were built there, water-cooled, far more powerful than Chicago Pile 1, designed to irradiate tons of uranium and breed plutonium. The plutonium was then chemically separated in massive processing canyons, buildings so radioactive that all work had to be done by remote control, behind thick concrete walls. So by 1944, the Manhattan Project had two parallel streams converging toward the same goal: enriched uranium-235 from Oak Ridge and plutonium-239 from Hanford. Both were being shipped to Los Alamos, where Oppenheimer's team faced what might have been the hardest problem of all: actually designing a device that would work reliably in a fraction of a second, converting a few kilograms of fissile material into an explosion equivalent to thousands of tons of TNT. And this is where the story splits into two very different engineering puzzles, because uranium and plutonium, despite both being fissile, turned out to behave differently enough that they demanded completely different bomb designs. Let's start with the simpler one: the uranium bomb. The concept behind it was almost deceptively straightforward. You take a mass of uranium-235 that's below critical, meaning it's not enough on its own to sustain a chain reaction, and you slam it together with another subcritical mass very fast so that the combined piece is supercritical. Boom. Chain reaction runs away. Energy release. Explosion. The design was called a gun-type assembly, and it worked exactly the way it sounds. You essentially built a modified artillery barrel, put one piece of uranium-235 at one end, and fired the other piece into it at high speed. When the two chunks met, you had a supercritical mass, and the chain reaction would take off. The physicists at Los Alamos were so confident this design would work that they never even tested it before using it. Think about that for a second. The first uranium gun-type bomb ever detonated was the one dropped on Hiroshima on August 6, 1945. They called it Little Boy. No prototype, no test shot. They simply had that much confidence in the physics. The design was robust, almost crude in its directness. The main engineering challenge was ensuring you could fire that uranium projectile fast enough, because if the two pieces came together too slowly, the chain reaction would start prematurely, generate some heat, and blow the assembly apart before most of the uranium had a chance to fission. You'd get a fizzle, a partial explosion, maybe equivalent to a few tons of TNT instead of thousands. Still devastating, but not the weapon they were building. So speed mattered. But conventional artillery propellants were fast enough for uranium. The gun-type design worked. Plutonium, though. Plutonium was a nightmare. And this is where the story gets really dramatic, because the entire direction of the project pivoted on a single, unwelcome discovery. Here's what happened. When plutonium-239 is produced in a reactor, it doesn't come out perfectly pure. Some of the plutonium-239 atoms absorb an additional neutron and become plutonium-240. And plutonium-240 has a nasty property. It undergoes spontaneous fission at a much higher rate than plutonium-239 or uranium-235. What that means is that a chunk of plutonium from a reactor is constantly spitting out stray neutrons, all on its own, without anyone asking it to. And that created a fatal problem for the gun-type design. Remember, the gun method works by slamming two pieces together, but that process takes a certain amount of time, maybe a millisecond or so. With plutonium-240 contamination generating all those background neutrons, the odds were overwhelming that a stray neutron would trigger a premature chain reaction during that millisecond before the two pieces had fully come together. You'd get a fizzle every time, not a full explosion, just an expensive radioactive mess. This realization hit Los Alamos in the spring and summer of 1944, and it was genuinely a crisis. They'd been planning to use the gun-type design for both uranium and plutonium. Suddenly, half their fissile material, the plutonium coming out of Hanford at great expense, was useless with the only bomb design they had. Oppenheimer had to make a decision fast, and the decision he made reshaped the entire laboratory. There was another approach, one that had been explored on the side by a brilliant and somewhat prickly physicist named Seth Nettermeyer. Nettermeyer had been experimenting with implosion, the idea that instead of slamming two pieces together in a line, you could surround a sphere of plutonium with conventional explosives and detonate them all simultaneously, crushing the plutonium inward, compressing it to a higher density. And here's the key insight. When you compress fissile material, you make it denser, and denser material reaches criticality at a smaller total mass. You're essentially squeezing the atoms closer together so the neutrons have less distance to travel before hitting another nucleus. The chain reaction becomes easier to start and harder to stop. If you could compress a subcritical sphere of plutonium fast enough and uniformly enough, it would go supercritical, and the chain reaction would race through the material before it had time to blow itself apart. The concept was elegant. The execution was almost impossibly difficult. The problem was symmetry. You needed the implosion to be perfectly spherical. Every point on the surface of that plutonium core had to be driven inward at exactly the same speed, at exactly the same moment. If one part of the explosive went off a microsecond early or pushed slightly harder than another part, the plutonium would squirt out sideways like a watermelon seed squeezed between your fingers. No symmetric compression, no supercritical mass, no weapon. And making explosives detonate with that kind of precision was something nobody had ever done before. Nettermeyer's early experiments with imploding metal cylinders were, frankly, discouraging. The cylinders came out looking like crumpled beer cans, lumpy, asymmetric, useless. This is where Oppenheimer brought in George Kistiakowsky, a Ukrainian-born chemist and explosives expert from Harvard. Kistiakowsky and Nettermeyer clashed almost immediately. Two strong personalities with very different approaches. And eventually Kistiakowsky essentially took over the implosion program. He assembled a team that included some of the best explosive engineers in the country, and they began developing what are called explosive lenses. The idea is borrowed from optics. A glass lens takes light waves coming from different directions and focuses them into a single point. An explosive lens does the same thing with a detonation wave. You use two different types of explosive, one fast-burning, one slow-burning, shaped and fitted together so precisely that the detonation wave, which starts at multiple points on the outside of the sphere, gets refocused into a single, perfectly converging spherical wave moving inward. Each lens had to be cast and machined to extraordinary tolerances. The geometry was worked out through a combination of theoretical calculations and endless testing, firing shot after shot at the test ranges around Los Alamos, using high-speed cameras and X-ray flash photography to see exactly how the implosion wave was behaving. And there was another innovation that helped make it work, a concept developed by the physicist Robert Christie. Originally, the plan had been to implode a hollow shell of plutonium. Christie argued that a solid sphere would actually work better. A solid core, compressed uniformly, would achieve a more reliable supercritical state. The design became known as the Christie pit, or the Christie gadget, and it simplified things enough to make the engineering tractable. The solid plutonium core at the heart of the device was about the size of a softball, roughly the size you could hold in your hand, warm to the touch from its own radioactive decay. Now, surrounding that core was a shell of natural uranium called a tamper. The tamper served two purposes. First, its sheer mass and inertia helped hold the core together for a few extra fractions of a microsecond as the chain reaction ran. And in those fractions of a microsecond, enormously more energy was released. Second, the tamper reflected neutrons back into the core, improving the efficiency of the chain reaction. Outside the tamper sat the explosive lenses, 32 of them, fitted together like the panels of a soccer ball, each one precisely shaped, and on the outside of each lens, a detonator. All 32 detonators had to fire within a microsecond of each other. The electronics to achieve that kind of simultaneous triggering were themselves a major engineering challenge developed by a group under Luis Alvarez. So you can see the layers of difficulty here. The implosion bomb, they called it Fat Man, was a far more complex device than Little Boy. And unlike the uranium gun type, nobody was confident enough to skip testing it. Which brings us to Trinity. The test was set for July 16, 1945, at a patch of desert in southern New Mexico called the Jornada del Muerto, the Journey of the Dead Man. The name was Old Spanish, referring to the waterless stretch of the Camino Real, but it carries an unintentional weight given what was about to happen there. The device was hoisted to the top of a 100-foot steel tower. Observation bunkers were set up at 10,000 yards, about 5.5 miles, north, south, and west. The base camp was 10 miles away. Nobody was entirely sure what the yield would be. Estimates varied wildly. Enrico Fermi, in his characteristically playful way, was offering side bets on whether the bomb would ignite the atmosphere, a possibility that had been studied and ruled out theoretically. But the fact that anyone was even joking about it tells you something about the uncertainty in the air. The detonation happened at 5:29 in the morning. Local time. The flash was visible over 100 miles away. The fireball expanded, rose, turned the pre-dawn darkness into something brighter than noon. The shockwave knocked people down at base camp. The steel tower simply vanished, vaporized. The sand beneath it was fused into a glassy, slightly radioactive substance they later called trinitite, a pale green glass that you can still find fragments of today. The yield was estimated at about 21 kilotons, 21,000 tons of TNT equivalent. From a sphere of plutonium you could cup in your hands. Oppenheimer later said that a line from the Bhagavad Gita came to his mind. Now I am become death, the destroyer of worlds. Kenneth Bainbridge, the test director, said something more plainly. Now we are all sons of bitches. The reactions among the scientists were mixed. Elation that the device worked, awe at its power, and for some, an immediate visceral dread about what they had created. 3 weeks later, on August 6th, Little Boy was dropped on Hiroshima. 3 days after that, on August 9th, a Fat Man implosion device was dropped on Nagasaki. The combined death toll, from the immediate blasts, the fires, and the radiation sickness that followed in the weeks and months after, is estimated at somewhere between 130,000 and 226,000 people, most of them civilians. Japan announced its surrender on August 15th, and then the war was over, and the world had to figure out what to do with this thing it had built. The scientists who had worked on the bomb scattered in different directions, some back to universities, some into government advisory roles, some into advocacy for international control of atomic energy. Oppenheimer himself became the most famous scientist in America, the face of the atomic age, appointed chairman of the General Advisory Committee of the newly created Atomic Energy Commission. He argued passionately for international cooperation, for openness, for putting nuclear energy under civilian and international control rather than letting it become purely a military tool. But there was another question looming, one that would tear the physics community apart and reshape global politics for the next half-century. Could you build something even bigger? Not a fission bomb, but a fusion bomb, a weapon that used the energy of a fission explosion to ignite a thermonuclear reaction, fusing light elements together the way the sun does, releasing energy on a scale that made even Hiroshima look small. The idea had been floating around Los Alamos almost from the beginning. Edward Teller, a Hungarian-born physicist with enormous talent and an equally enormous ego, had been pushing for a thermonuclear weapon, what he called the super, since 1942. During the war, Oppenheimer had to keep redirecting Teller back to the fission bomb work because Teller kept wanting to leap ahead to the bigger prize. And now, with the war over and the Soviet Union emerging as a rival superpower, the question of whether to pursue the hydrogen bomb became one of the most explosive political and moral debates in the history of science. And it's worth slowing down here, because what happened next tells you so much about how the relationship between physics and power actually works, how the people who understand the science best can find themselves completely overruled by the people who control the politics. So let's talk about Teller's super. The basic idea is, on the surface, almost poetically simple. You know how fission works. You split heavy atoms and release energy. Fusion is the opposite. You take the lightest atoms, hydrogen isotopes, and you slam them together so hard that they fuse into helium, and in the process they release even more energy per unit of mass than fission does. This is what powers the sun. This is what powers every star you can see when you look up at night. The temperatures and pressures at the core of the sun are so extreme that hydrogen nuclei, which are just protons, overcome their electrical repulsion and merge. And when they do, a tiny bit of mass converts into a tremendous amount of energy, just like Einstein's equation predicts. The challenge, of course, is that to make fusion happen, you need those insane temperatures, tens of millions of degrees. On Earth, the only way anyone in the 1940s could imagine reaching those temperatures was with a fission bomb. So the concept was, essentially, a fission bomb as a trigger, a match, to ignite a much larger fusion fuel load. A bomb to set off a bomb. Now, Teller had been thinking about this since the summer of 1942, back at the Berkeley conference where Oppenheimer first gathered theorists to discuss bomb design. Teller actually derailed part of that conference by raising the possibility that a fission bomb might ignite the nitrogen in the atmosphere or the hydrogen in the ocean, just set the whole planet on fire. Hans Bethe and others ran the calculations and showed that couldn't happen. The temperatures would dissipate too quickly. But the fact that they had to check tells you something about the energies they were dealing with. And Teller, having been reassured the world wouldn't end, pivoted immediately to asking, well, could we harness fusion deliberately? Could we build a bomb with no theoretical upper limit on its yield? During the war years, Teller sketched out what became known as the classical super design. The idea was that a fission bomb would detonate at one end of a long cylinder filled with liquid deuterium. That's heavy hydrogen, hydrogen with one extra neutron. The fission explosion would heat the deuterium enough to start fusion reactions, and then those reactions would propagate down the cylinder, like a flame burning along a fuse. More deuterium, bigger explosion. In principle, you could make it as large as you wanted. There was no critical mass limit the way there was with fission. You just kept adding fuel. But here's the thing, and this is crucial. Nobody could actually prove the classical super would work. The physics of thermonuclear ignition and burn was extraordinarily complex, far beyond what anyone could calculate by hand. Would the fusion reaction actually propagate, or would the deuterium blow apart before enough of it could fuse? Teller believed it would work. Others weren't so sure. And this uncertainty sat right at the center of the political firestorm that followed. In August 1949, the Soviet Union detonated its first atomic bomb, years earlier than most American intelligence estimates had predicted. The news hit Washington like a thunderclap. Suddenly, the American monopoly on nuclear weapons was over, and almost immediately, there was pressure from military leaders, from hawkish politicians, from Teller himself, to race ahead to the hydrogen bomb, to restore American superiority with a weapon so powerful that no one could match it. Oppenheimer's General Advisory Committee was asked to weigh in. In October 1949, they met and delivered a unanimous recommendation against a crash program to build the hydrogen bomb. Their reasoning was partly technical. They weren't convinced the super would work, and partly moral. The report, much of it written by Oppenheimer and the physicist James Conant, argued that a thermonuclear weapon would be a weapon of genocide, useful only for destroying entire cities, with no legitimate military target that couldn't already be addressed by fission bombs. They called it a weapon of unlimited destructive power, and they said that pursuing it would set off an arms race that would leave the world less safe, not more. Think about what that took. These were scientists telling the President of the United States, in the middle of a Cold War panic, that America should not build the most powerful weapon it was capable of building. That restraint, they argued, was the better strategy. It didn't matter. On January 31st, 1950, President Truman announced that the United States would proceed with development of the hydrogen bomb. The political pressure was simply too great. The Soviet threat felt too immediate. And Teller, who had lobbied relentlessly for the program, finally had his mandate. But here's where the story takes a turn that's both scientifically fascinating and deeply human. Even with Truman's green light, the classical super still didn't work. Through 1950, a brilliant mathematician named Stanislaw Ulam, a Polish émigré who had worked at Los Alamos during the war, ran a series of calculations, some of the first done on early electronic computers, that showed the classical super design would fail. The fusion reaction simply wouldn't propagate. The deuterium would disperse before enough of it could burn. Teller's design, the one he'd been championing for nearly a decade, was a dead end. You can imagine how Teller took that news. Not well. But Ulam didn't just deliver bad news. He also delivered the solution, or at least the seed of one. In early 1951, Ulam had an insight. Instead of trying to heat the fusion fuel directly with the fission explosion, what if you use the radiation from the fission primary, the X-rays, which travel at the speed of light, to compress the fusion fuel first? Compression before heating. If you could squeeze the deuterium to extraordinary densities, fusion would ignite far more easily because the nuclei would be packed so closely together that they couldn't help but collide. Teller immediately grasped the significance and refined the concept. What emerged was the Teller-Ulam design, and it's one of the most consequential engineering ideas in human history. The basic architecture, and this is now declassified so we can talk about it, involves two stages. The primary is a fission bomb, an implosion device like Fat Man. The secondary is a separate capsule containing fusion fuel, typically lithium deuteride in later designs, surrounding a central rod of fissile material called the spark plug. Both stages are enclosed in a heavy casing, often made of uranium. When the primary detonates, it fills the interior of the casing with X-ray radiation, an incredibly intense bath of energy. That radiation pressure compresses the secondary stage inward, squeezing the fusion fuel to enormous density. The compression also drives the spark plug past criticality, so it undergoes fission, heating the fusion fuel from the inside at the same time the radiation is crushing it from the outside. And then fusion ignites. The temperatures reach hundreds of millions of degrees. Deuterium and tritium nuclei fuse into helium, releasing neutrons and energy on a scale that dwarfs the fission primary. The elegance of it, if you can call a weapon of mass destruction elegant, is that the radiation does the work of compression at the speed of light, far faster than the physical blast wave that would otherwise blow everything apart. It's a race between assembly and disassembly, just like in a fission bomb. But now, the assembly mechanism is radiation implosion, and it's fast enough to win. The first test of this concept was Ivy Mike, detonated on November 1, 1952, at Eniwetok Atoll in the Pacific. It used liquid deuterium as its fusion fuel, which required a massive cryogenic refrigeration plant. The whole device weighed about 82 tons, so it was hardly a deliverable weapon. But it worked. The yield was 10.4 megatons. That's roughly 700 times the energy of the Hiroshima bomb. The fireball was over 3 miles wide. The mushroom cloud rose to over 100,000 feet. The island of Alujalab, where the device sat, simply ceased to exist. It was replaced by an underwater crater, more than a mile across and 200 feet deep. 10 months later, in August 1953, the Soviet Union tested a device that used lithium deuteride, a solid fusion fuel far more practical than liquid deuterium, in a design developed by Andrei Sakharov and his colleagues. It yielded about 400 kilotons, not a true staged thermonuclear weapon yet, but it showed the Soviets were close. And by November 1955, they tested a genuine multi-megaton hydrogen bomb. The arms race Oppenheimer had warned about was fully underway. And this brings us to one of the saddest chapters in the whole story. What happened to Oppenheimer himself? His opposition to the hydrogen bomb had made powerful enemies. Teller resented him. Lewis Strauss, the chairman of the Atomic Energy Commission, distrusted him. And in the paranoid atmosphere of McCarthyism, Oppenheimer's past associations with left-wing causes and Communist Party members, associations that had been known and accepted during the war, were suddenly reframed as evidence of disloyalty. In December 1953, his security clearance was suspended. In the spring of 1954, he was subjected to a grueling hearing before a personnel security board where his entire life was dissected, his loyalty questioned, his private conversations, recorded by FBI surveillance, read back to him. Teller testified against him, saying that while he didn't question Oppenheimer's loyalty, he would prefer to see the country's security in other hands. It was a devastating blow. The board voted 2-1 to revoke Oppenheimer's clearance. The man who had led the creation of the atomic bomb was effectively declared a security risk by the government he had served. It was a political purge dressed up as a security proceeding, and most of the physics community knew it. Oppenheimer was never charged with espionage, never accused of passing secrets. His crime was having been right about the hydrogen bomb being a moral catastrophe, and having had the courage to say so to people who didn't want to hear it. He retreated to the Institute for Advanced Study in Princeton, where he had been director since 1947, and lived out his remaining years in a kind of dignified exile. He died of throat cancer in 1967, at 62. In 2022, the U.S. Department of Energy formally vacated the 1954 decision, acknowledging that the process had been flawed and driven by political animus. A small gesture, decades too late, but the thermonuclear genie was out of the bottle, and the scale of what humanity could now do to itself was almost incomprehensible. The largest nuclear weapon ever detonated was the Soviet Tsar Bomba, tested on October 30th, 1961, over the Arctic archipelago of Novaya Zemlya. It yielded approximately 50 megatons, 50 million tons of TNT equivalent. The original design could have produced 100 megatons, but Sakharov and his team deliberately scaled it back by replacing the uranium tamper with lead, which reduced the yield but also cut the radioactive fallout dramatically. Even at 50 megatons, the flash was visible 600 miles away. The shock wave circled the Earth 3 times. Windows shattered in Finland and Norway, hundreds of miles from ground zero. The mushroom cloud rose 40 miles into the sky. And here's what's worth sitting with for a moment. The Tsar Bomba was a demonstration, a political statement. It was never intended as a practical weapon. It was too large, too heavy, too unwieldy. But it proved a point about what was possible, and that point reshaped everything. Because once you know that a single device can flatten everything within a 30-mile radius and spread lethal fallout across thousands of square miles, the entire calculus of war changes. This is the world that nuclear physics built, for better and for worse, and the scientists and engineers who understood it best were the ones most haunted by what they had created. And that haunting, that weight of knowledge, didn't just sit quietly in their minds. It spilled outward into policy, into activism, into a decades-long struggle to figure out how humanity could live alongside the thing it had invented. Because that was the new problem, wasn't it? Not how to build the bomb. That part was done. The problem now was how to survive it. And this is where nuclear physics stops being purely a story about particles and reactions and starts becoming a story about systems, about reactors, about treaties, about proliferation, about the strange and sometimes beautiful ways that the same physics, which could destroy a city, could also light one up. So let's talk about that. Let's talk about what happened when the world tried to take this terrifying force and put it to work. The idea of using nuclear fission for power generation wasn't new. It had been floating around since before the war. You remember Fermi's Chicago Pile 1, that first sustained chain reaction in December 1942. Even then, people understood that a controlled chain reaction produces heat, and heat can boil water, and steam can turn turbines, and turbines generate electricity. The basic logic was almost embarrassingly simple. The challenge was everything else. How do you control the reaction precisely enough that it doesn't run away from you? How do you extract the heat efficiently? How do you shield everyone from the radiation? How do you deal with the waste? Enrico Fermi himself had thought about reactors for power, but during the war, The only goal was producing plutonium for weapons. The reactors at Hanford were industrial plutonium factories. They generated enormous amounts of heat, and that heat was simply dumped into the Columbia River. Nobody cared about capturing it. There was a war to win. But after the war, the landscape shifted. In 1946, the U.S. passed the Atomic Energy Act, which transferred control of nuclear technology from the military to a new civilian agency, the Atomic Energy Commission, the AEC. And within the AEC, and within the national laboratories that had grown out of the Manhattan Project, engineers and physicists started seriously asking, can we build a reactor that generates useful electricity? The answer came on December 20th, 1951, at a facility called the Experimental Breeder Reactor 1, or EBR-1, in the Idaho desert. It was a small reactor, cooled by a liquid metal, a sodium-potassium alloy, and it used fast neutrons rather than the thermal neutrons that most reactors would later rely on. On that December day, the reactor produced enough electricity to power 4 light bulbs. 4 light bulbs. That was it. But someone chalked a message on the wall of the reactor building. Electricity was first generated here from atomic energy. And they were right. It was a beginning. Now, 4 light bulbs is a charming story, but it's not exactly powering a city. The real push toward nuclear power came from an unlikely direction: submarines. Here's the thing about conventional submarines in the 1940s and early 1950s. They weren't really submarines. They were surface ships that could temporarily submerge. Their diesel engines needed air, so they had to surface regularly, or at least snorkel near the surface, to run the engines and recharge their batteries. A true submarine, one that could stay underwater indefinitely, needed a power source that didn't require oxygen, and a nuclear reactor fit that description perfectly. The person who drove this idea into reality was Hyman Rickover, and he's one of the most fascinating and difficult figures in the entire nuclear story. Rickover was a captain in the U.S. Navy, eventually an admiral, and he was, by all accounts, brilliant, relentless, abrasive, and nearly impossible to work with. He demanded perfection from everyone around him, and had no patience for bureaucracy, incompetence, or excuses. He was the kind of leader who would personally review the academic transcripts of every officer assigned to his program. He once made an interviewee sit in a chair with the front leg shortened so the candidate would slowly slide forward during the entire conversation, just to see how they handled discomfort. But Rickover understood something crucial. He understood that a naval reactor had to be absolutely, uncompromisingly reliable. On a submarine, you can't evacuate. You can't call for help. You're sealed inside a steel tube hundreds of feet underwater, and the reactor is right there with you. So the engineering had to be flawless. And Rickover built an organization, the Naval Reactors Branch, that became legendary for its engineering discipline, its safety culture, and its zero tolerance for shortcuts. The reactor design Rickover championed used pressurized water as both the coolant and the moderator. Here's how that works. You have fuel rods, uranium enriched to a higher level than commercial reactors would later use, and those fuel rods are surrounded by ordinary water. The water serves 2 purposes. First, it slows down the neutrons. That's the moderation, making them more likely to cause fission in uranium-235. Second, the water carries away the heat generated by the fission reactions. But here's the clever part. The water in the primary loop is kept under very high pressure, something like 150 atmospheres, so it doesn't boil even though it gets extremely hot, over 300 degrees Celsius. This superheated pressurized water then flows through a heat exchanger called a steam generator where it transfers its heat to a secondary loop of water that is at lower pressure. That secondary water boils, produces steam, and the steam drives a turbine. The primary water, which has been in contact with the reactor and is radioactive, never touches the turbine. It stays in its own sealed loop. Elegant, right? Two loops, one hot and pressurized, one producing steam, and a wall of metal between them, keeping the radioactivity contained. The first nuclear-powered submarine, USS Nautilus, launched in January 1954 and went to sea in early 1955, and it changed naval warfare overnight. Nautilus could stay submerged for weeks at a time, limited only by the crew's food supply and psychological endurance, not by fuel. In 1958, Nautilus made the first submerged transit of the North Pole, traveling under the Arctic ice cap, something no diesel submarine could have dreamed of attempting. The pressurized water reactor design that Rickover's team perfected for submarines became the foundation for most of the world's commercial nuclear power plants. That's worth pausing on. The reactor design that generates roughly 10% of the world's electricity today traces its lineage directly back to the engineering challenge of powering a submarine. The first commercial nuclear power plant in the United States was Shippingport in Pennsylvania, which went critical in December 1957. It used a pressurized water reactor, essentially a scaled-up version of the submarine design, and it fed electricity into the grid for the Duquesne Light Company. Other countries were moving fast too. The United Kingdom had already connected Calder Hall in Cumberland to the national grid in 1956, making it arguably the world's first commercial nuclear power station, though it also produced plutonium for weapons, which complicates the commercial label a bit. The Soviet Union had connected a small reactor at Obninsk to the grid even earlier. In 1954, though at only 5 megawatts electrical, it was more of a demonstration than a power plant. And then came the boom. Through the 1960s and into the 1970s, nuclear power expanded rapidly, especially in the United States, France, the United Kingdom, the Soviet Union, and Japan. The promise was extraordinary. Electricity too cheap to meter, as Louis Strauss, the IAEA chairman, famously said in 1954. Though historians debate whether he was actually talking about fusion rather than fission. Either way, the optimism was real. Nuclear power seemed like the answer to everything. Abundant energy, no air pollution, no dependence on foreign oil. Utilities ordered reactors by the dozen. By the mid-1970s, the United States alone had over 50 reactors operating and many more under construction. But here's where the story gets complicated, because nuclear power carried with it a set of problems that no other energy source had ever posed. The waste, for one. When uranium fuel is used in a reactor, the fission process creates a zoo of radioactive byproducts. Cesium-137, strontium-90, iodine-131, and dozens of others, plus transuranic elements like plutonium and americium. Some of these isotopes remain dangerously radioactive for thousands of years, tens of thousands of years, and nobody had, or has, a fully satisfactory answer for what to do with them. The plan was always, we'll figure it out later, and later kept getting pushed further down the road. The United States spent decades and billions of dollars studying Yucca Mountain in Nevada as a permanent repository, and as of now, that project is essentially stalled, caught in a web of political opposition and legal challenges. The waste sits in spent fuel pools and dry cask storage at reactor sites across the country, waiting for a destination that may never come. And then there were the accidents. The physics that makes a nuclear reactor work, the chain reaction, the intense radioactivity, the enormous energy densities, also makes it uniquely dangerous when things go wrong. And things did go wrong. The first major accident that captured public attention happened on March 28, 1979, at 3 Mile Island, a nuclear power plant near Harrisburg, Pennsylvania. Unit 2, a pressurized water reactor that had only been operating for about 3 months, experienced a partial meltdown. What happened was a cascade of mechanical failures, design flaws, and human errors that fed on each other. A valve stuck open, draining coolant from the reactor vessel. The operators, confused by misleading instrument readings, actually made things worse by reducing the flow of emergency cooling water, not realizing that the core was uncovering. By the time they understood what was happening, roughly half the core had melted. The containment building held. That thick concrete and steel shell did its job, and the actual release of radioactivity to the environment was small. No one died, but the psychological impact was enormous. The public's trust in nuclear power, already shaky, cracked. New reactor orders in the United States effectively stopped. The regulatory landscape changed dramatically, and the nuclear industry entered a long, slow period of stagnation in the West. 7 years later, something far worse happened, and it happened in a very different kind of reactor, in a very different political system. On April 26, 1986, at the Chernobyl nuclear power plant in the Ukrainian Soviet Socialist Republic, reactor number 4 exploded, and it exploded in a way that no Western reactor could have, because of fundamental differences in design and in the culture surrounding that design. The reactor at Chernobyl was an RBMK, a Soviet acronym that translates roughly to High Power Channel Type Reactor. It was a design unique to the Soviet Union, and it had characteristics that Western engineers had long considered unacceptable. The most important of these was a positive void coefficient of reactivity. Now, that's a mouthful, but the idea is actually straightforward. In a pressurized water reactor, the kind Rickover developed, the kind at 3 Mile Island, water serves double duty. It cools the fuel, and it also moderates the neutrons, slowing them down so they can sustain the chain reaction. If you lose the water, you lose your moderator, and the chain reaction slows down or stops. The reactor has a kind of built-in safety feature. Lose your coolant, lose your reactivity. But the RBMK used graphite as its moderator, not water. Water was there just for cooling. And here's the dangerous part. In certain operating conditions, if the water started to boil and turn to steam, forming voids, basically bubbles, the reactor actually became more reactive, not less. More bubbles meant more neutrons hitting the fuel, which meant more heat, which meant more bubbles, which meant even more reactivity. It was a positive feedback loop, a vicious circle. And on the night of April 26th, the operators were conducting a safety test. Ironically, a test designed to see how long the turbines would spin and provide power during a shutdown. But to run the test, they had to bring the reactor to a low power state, and they did it badly. The power dropped far lower than intended, almost to zero, and the reactor entered a poisoned condition. Xenon 135, a fission product, was absorbing neutrons and suppressing the reaction. To compensate, the operators withdrew nearly all the control rods, far more than safety rules allowed. They were essentially flying blind, with almost no margin for error, in a reactor that was inherently unstable at low power. When they initiated the test and the coolant pump slowed, the water began to boil. The positive void coefficient kicked in. Power surged, not gradually, but exponentially. In the space of a few seconds, The reactor's thermal output spiked to perhaps 100 times its normal maximum. The fuel shattered. Steam pressure blew the 1,000-ton reactor lid off the building. A second explosion, likely a steam explosion, though some researchers have argued it may have involved hydrogen, tore the reactor apart entirely and sent burning chunks of graphite and reactor fuel across the plant grounds. The graphite moderator caught fire, and because the RBMK had no containment building, nothing like that thick concrete shell that had held at 3 Mile Island, there was nothing between the burning, exposed reactor core and the open sky. The immediate death toll was relatively small, 2 plant workers killed in the explosions, and within weeks, 28 emergency responders died of acute radiation syndrome. These were the firefighters and plant operators who rushed to the scene, many of them not fully understanding what they were being exposed to. Some of them picked up chunks of graphite from the reactor with their bare hands. The heroism was real, and the cost was terrible. But the longer-term consequences spread across an entire continent. A plume of radioactive material, iodine-131, cesium-137, strontium-90, drifted across Belarus, Ukraine, Scandinavia, and Western Europe. Over 100,000 people were evacuated from the surrounding area. The city of Pripyat, built specifically to house the plant's workers and their families, was abandoned and remains a ghost town to this day. The long-term health effects, thyroid cancers, particularly in children exposed to iodine-131, are still being studied and debated, but the World Health Organization documented a dramatic spike in childhood thyroid cancer in the affected regions. Chernobyl became a word that meant something far beyond a place name. It became shorthand for technological hubris, for the dangers of a system where safety concerns could be overridden by institutional pressure, where operators could disable safety systems because the test schedule demanded it, where the fundamental design flaws of a reactor were treated as acceptable because acknowledging them would have been politically inconvenient. The Soviet system's culture of secrecy made it worse. The government initially tried to suppress information about the disaster, and it was Swedish monitoring stations detecting elevated radiation levels that first alerted the outside world. And then, a quarter-century later, it happened again, in a completely different way, in one of the most technologically advanced nations on Earth. On March 11, 2011, a magnitude 9.0 earthquake struck off the coast of Japan, one of the most powerful earthquakes ever recorded. The Fukushima Daiichi nuclear power plant, operated by Tokyo Electric Power Company on the northeast coast of Honshu, had 6 boiling water reactors. When the earthquake hit, the 3 operating reactors shut down automatically. The control rods inserted, the chain reaction stopped. The system worked exactly as designed. But here's the thing about nuclear reactors. Even after you shut down the chain reaction, the fuel keeps producing heat. Decay heat, it's called. All those radioactive fission products in the fuel are still decaying, still releasing energy. And in the first hours after shutdown, that heat can be substantial, several % of the reactor's full thermal output. You need to keep cooling the fuel, or it will overheat and melt, even with the chain reaction stopped. And to run the cooling pumps, you need electricity. The earthquake knocked out the external power grid. That was expected. The plant had backup diesel generators for exactly this scenario. But about 45 minutes after the earthquake, a massive tsunami, with waves over 14 meters high, swept over the plant's seawall, which had been designed for a much smaller wave. The tsunami flooded the basements where the diesel generators were housed and destroyed them. It also knocked out the electrical switching equipment. The plant lost all AC power. This condition, called station blackout, was supposed to be almost impossibly unlikely. But it happened, and without power, the operators couldn't run the pumps. They couldn't circulate cooling water. The decay heat kept building. Over the next several days, the cores of 3 reactors melted. Hydrogen gas, generated when the superheated zirconium cladding on the fuel rods reacted with steam, accumulated in the reactor buildings and exploded, blowing apart the upper structures in dramatic blasts that were broadcast on television worldwide. Radioactive material was released into the atmosphere and the ocean. Over 150,000 people were evacuated from the surrounding area. Unlike Chernobyl, no one died from acute radiation exposure, and studies suggest the long-term health effects from radiation will be small. But the economic and social damage was enormous. The trauma to the displaced communities was real, and the impact on public confidence in nuclear power was devastating, particularly in Japan and Germany. Germany, in fact, decided to phase out nuclear power entirely in the wake of Fukushima, shutting down its last 3 reactors in April 2023. Japan itself took all its reactors offline for years of safety reviews, and only a fraction have restarted. The global nuclear industry, which had been talking about a nuclear renaissance in the years before Fukushima, found itself once again on the defensive. And yet, here's where the story takes a turn that I think is genuinely fascinating, because the arguments for nuclear power didn't go away. If anything, they got stronger, driven by a force that the pioneers of nuclear physics never anticipated: climate change. The burning of fossil fuels, coal, oil, natural gas, releases carbon dioxide, and that carbon dioxide is warming the planet. And when you look at the numbers, really look at them, nuclear power is one of the lowest carbon sources of electricity we have. A nuclear plant, once built, produces essentially 0 carbon emissions during operation. Per unit of energy generated, nuclear power causes fewer deaths than coal, fewer than oil, fewer than natural gas, and by some analyses, fewer even than wind and solar when you account for the full life cycle of manufacturing, mining, and installation. The waste problem is real, but the volume of waste is remarkably small. All the spent fuel ever produced by all the nuclear plants in the United States would fit on a single football field stacked less than 10 meters high. Compare that to the billions of tons of carbon dioxide pumped into the atmosphere every year by fossil fuel plants. So in the 2020s, something unexpected started happening. Countries that had been skeptical of nuclear power began reconsidering. France, which had long generated about 75% of its electricity from nuclear plants, doubled down. The United Kingdom announced plans for new reactors. Even the United States, where no new reactor had been completed in decades, saw the Vogtle units 3 and 4 come online in Georgia. Massively over budget and behind schedule, yes, but operational. And a whole new generation of reactor designs began attracting serious investment. Small modular reactors, or SMRs, promised to be factory-built, cheaper, and safer than the giant gigawatt-scale plants of the past. Some designs use molten salt as a coolant. Others use high-temperature gas. Some are designed to run on thorium instead of uranium. A few startups are even pursuing fusion, that dream of recreating the process that powers the sun, fusing light atoms together instead of splitting heavy ones apart. And fusion, that brings us full circle in a beautiful way. Because fusion is where all of this started, in a sense. It was Eddington, back in the 1920s, who first suggested that the sun's energy came from the fusion of hydrogen into helium. It was the quantum mechanical understanding of tunneling, particles crossing barriers they shouldn't classically be able to cross. That explained how fusion could happen at the temperatures inside a star. And it was the hydrogen bomb, the Teller-Ulam design, that first demonstrated uncontrolled fusion on Earth. The dream of controlled fusion, harnessing that energy gently, steadily, to generate electricity, has been pursued since the 1950s. The joke in the field has always been that fusion is 30 years away, and always will be. But in December 2022, researchers at the National Ignition Facility at Lawrence Livermore National Laboratory achieved something that had never been done before. They fired a bank of lasers at a tiny pellet of deuterium and tritium and got more energy out of the fusion reaction than the lasers put in. Ignition. It was a proof of concept, not a power plant. The lasers themselves consumed far more energy than they delivered, but it was a milestone that had been chased for decades. Whether fusion ever becomes practical for electricity generation is still an open question. The engineering challenges are staggering. You need to confine a plasma at 100 million degrees, hotter than the center of the sun, and hold it stable long enough for the fusion reactions to sustain themselves. The leading approach, the tokamak, uses incredibly powerful magnetic fields to contain the plasma in a donut-shaped chamber. The biggest tokamak ever built, ITER, is under construction in southern France, a collaboration of 35 nations, and it's designed to produce 10 times more fusion power than it consumes. If it works as planned, it could demonstrate the feasibility of fusion power by the mid-2030s. But whether the future is fission, fusion, or some combination we haven't imagined yet, the story we've traced tonight, from Democritus wondering what you'd find if you kept cutting matter in half, through Rutherford's gold foil experiment, through Bohr's quantum atom, through Chadwick's neutron, through Hahn and Strassmann's barium, through Meitner and Frisch's walk in the snow, through Fermi's squash court in Chicago, through the blinding light over Alamogordo and the horror of Hiroshima and Nagasaki, through the hydrogen bomb and the long, cold shadow of mutually assured destruction, through Rickover's submarine reactors and shipping port and the dream of electricity too cheap to meter, through 3 Mile Island and Chernobyl and Fukushima, through the slow, uncertain, complicated return to nuclear power, driven by the urgency of climate change, all of it traces back to that fundamental question about the nature of matter. What are things made of? What happens when you look closer? And closer still? Every chapter of this story was written by people. Curious, stubborn, brilliant, flawed, sometimes heroic, sometimes reckless people who wanted to understand how the universe works and then couldn't resist trying to use what they'd learned. Some of them changed the world for the better. Some of them unleashed forces they couldn't control. Most of them did both, often at the same time, and spent the rest of their lives trying to make sense of what they'd done. The atom is still there, of course, still doing what it's always done, holding together the matter that makes up everything you can touch, everything you can see, everything you are. The nuclei in your body were forged in stars that exploded billions of years ago, scattering their contents across space, and those contents eventually coalesced into a planet, and on that planet, into you. The nuclear physics we've talked about tonight isn't just history. It's the physics of starlight, of the warmth of the Earth's core, of the medical isotopes that help diagnose and treat disease, of the smoke detectors in your ceiling, of the age of ancient artifacts dated by carbon-14. It's woven into everything. So let that settle over you now, quietly, like the last warmth of a long conversation. The atoms in your pillow, in the air you're breathing, in the walls around you. Every one of them has a nucleus, and every one of those nuclei is a tiny, dense knot of energy, held together by forces that physicists spent a century learning to describe. You don't need to think about it. You don't need to remember all the names and dates. Just know that the world is more intricate, more beautiful, and more strange than it appears, and that understanding even a small part of it is one of the finest things human beings have ever done. Rest now. The atoms will take care of themselves.